Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore Newton's three laws of motion. Now Newton was probably one of the most famous scientists, and his contribution to physics basically is up there as one of the greatest that have been recorded in history. He was born December 25th in Woolsthorpe, Lincolnshire, which is in the UK, in 1642. Basically, as well as being a prolific mathematician, he came up with theories on optics and also put forward three laws to explain motion. Now, basically, we're going to explore those three laws and how they link with the forces that we mentioned in the previous video. So, Newton's first law basically is the law of inertia, and he basically stated that every body continues in a state of rest or uniform motion in a straight line unless a force is applied upon it or impressed upon it. Now, as I stated, this is basically called the term of inertia, and basically it's the resistance that the body has to any specific motion. So, for example, if you fired a bullet in space and the bullet was able to be propelled, it would keep moving at exactly the same speed as when it left the gun, regardless of what's in space, until a force is applied upon it. Now obviously if that bullet then hits like the space shuttle, for example, then a force is applied on that gun and the motion changes. But until that point happens, the result is it will continue and almost continue indefinitely until a force is applied. So as it says, a stationary object will try not to move. So if you think of any object, it will try and resist you. Now friction obviously helps with that. The bigger the object is, the more resistance there is to the change in motion. That's why if you think about a big truck, it requires a huge amount of force to actually get it rolling. Once you've got it rolling, it's very difficult to stop it. It still has inertia. It's still moving, but it's moving at a set speed, and as a result, it doesn't want to stop. So you need really good brakes in order to get that truck to stop. So Newton's first law of inertia is around us all the time, and it's literally about the fact that things will continue in their motion and they will try and resist a change in motion, so we have to apply a force upon it. Different objects obviously will do this to a varying degree of complexity. Obviously a pencil, very little inertia. A big tanker, shipping tanker, will have a huge amount of inertia. Okay, so his second law basically stated that in order to change the motion, i.e. in order to counteract inertia, you have to apply a force, and this force causes acceleration, or that change in speed. So if you think about a truck, it's standing still, you're going to have to put a force. That force is torque, which is the turning motion of the wheels, which is going to cause that truck to move. It's going to require a huge amount of torque to basically move that truck. If you were to take that truck and fill it up with huge amounts of substance, doesn't matter really what it was, you would need even more torque to actually change that force. Obviously, once it's moving, you're then going to need a greater force to actually move it in the opposite direction back to rest. So again, force is going to be required to cause that acceleration. And this is why at the beginning of this motion topic, I got you to learn the definitions of velocity and acceleration, because acceleration is a change in velocity, and we now know that a force has to be applied on an object to change that velocity. From this, Newton came up with one of his most famous equations, which is F equals ma. A force acting on a mass will cause it to accelerate or change the velocity. Notice that the mass in this case is going to be a constant, so if we were able to plot this, what we would get is F going up the vertical, A going along the horizontal, and the gradient of the line would actually be the mass. Now in this case, force is going to be measured as weight force in newtons, mass is going to be in kilograms, and acceleration is in meters per second. So we can apply this to also mass and weight. Now mass and weight is we use the terms almost incorrectly. Mass is basically the amount of substance we've got, and it's measured in kilograms. It's a constant value, as we know, wherever we go. So I'm 80 kilograms. If I go onto the moon, I'm still 80 kilograms. I've still got the same amount of matter. If I go to Jupiter, I'm still 80 kilograms. So my mass never changes. However, my weight does. Weight is actually a force, and it's the force of gravity which is acting upon this mass. So really, when we say, what is your weight? Really what we're asking is, what is the effect of gravity of the planet acting on your mass? Now, weight is a force, so as a result, weight should be measured in newtons. Now, you know, when we step on some bathroom scales, we always measure it in kilograms. Really, the reason why that is because gravity is the same over the surface of the planet. So the effect of gravity across the surface of the planet basically is the same, and we've converted it into kilograms so that we know how much mass we actually have contained, so that the units are changed. But if I'm 80 kilograms on this planet, then theoretically my weight force, is 800 newtons. And this is going to vary depending on the planet that I happen to be on. So if I went to stand on the moon has less gravity, which means that I would have less weight. If I go into outer space, there is no gravity at all, or very, very little. As a result, I would then be weightless because I haven't got gravity pulling on me. My mass is still the same though. I still weigh 80 I still have 80 kilograms of mass, but because I'm in outer space, no gravity is pulling upon me. As a result, I will be weightless. There will be no force of gravity acting on my mass. So from this, we can then rearrange Newton's formula to get weight force equaling mg, where obviously the force of weight, and you can see that with the little subscript w measured in newtons. The mass obviously will be in kilograms, but g will be the acceleration, and has been converted into g because it's acceleration due to gravity. On the planet Earth, that acceleration due to gravity is 9.81 meters per second. So from Newton's second law, I can now apply this to produce a weight force. So any object which is hanging down will have a weight force applied upon it. So as a result, we can start employing our forces in different dimensions on an object, and as a result, we can start calculating what is the effect of various forces as they are applied. Now, Newton's third law works on the idea that forces work in pairs, and for every action, there is always going to be an equal and opposite reaction. Well, let's take a golf club. Now, a golf club, basically, when it hits the ball, we are actually going to have an action, and then we're also going to have a reaction. Now, if you've ever played golf, you know that when you hit the ball, and if you hit the ball on the sweet spot, you'll actually feel some resonance actually going through the golf club shaft. It feels good. Why is that? Because the ball basically imparts some of the force of the club hitting it up through the shaft, and you feel it. So there must be a reaction of the golf ball on the club as well as the club hitting the ball. So when you go through your swing, a force is going to be applied upon the ball, and of course that ball moves off. But in the same way as it's making contact, we know that the force of the ball will impart a force backwards on the golf club. Now remember that if we go back to what we were talking about with respect to impulse, the ball has a very, very small mass, so it will have its momentum will be converted into mv. V will be really fast, m will be really small. So as a result, the momentums will be the same going in opposite directions, remembering that the law of conservation of momentum says that the momentum before equals the momentum after, but there's going to be less force applied upon the golf club because the ball is a lot smaller, and the mass of the golf club the ball is moving fast, but the mass of the golf club is really big. So when we combine those momentums, the result is that we get a small force being applied on the golf club. Let's look at this in a bigger scenario. Let's take the launch of the space shuttle. Now, the space shuttle, when it releases, when it moves up and it launches, basically uses Newton's third law. The action is the gases being expelled through the actual large engines or booster rockets that you can see there, which generates a huge amount of lift. So they're pushing downwards. The reaction of that is that the ground pushes the rocket upwards as it pushes on the gas. It's almost like a spring, causing it to push off. So as it's pushed out, it then pushes off in the same direction. So we get this action and reaction occurring. So what we have to be able to do is to take Newton's 3 laws and start applying them to various scenarios. We've got the rule of inertia, which is Newton's first law. We've got a force applying on a mass will change its velocity, hence causing it to accelerate, and that can be linked to the concept of weight force. And then so that's Newton's second law. And then we've got the idea that Newton's third law is action and reaction. For every action, there's an equal and opposite reaction which is going to be applied. So we've already talked about force, weight and gravity. So what we're going to do is to set up a variety of different scenarios and try and see how we can combine different weight forces and gravity and support forces and basically see what happens. So this is how we're going to draw it. We're going to work on the principle that we've got Fn is going to be a normal force, or what we would call a support force. We're then going to have Fw, which is a weight force, and we're going to have Fa, which is going to cause our acceleration. So what we're going to do is imagine that we're standing on a set of scales in an elevator. So if we want to have a balanced stationary force, what we will notice that on the scales, we're going to have weight force acting down, and then the scales are going to produce the same force acting up, which is going to be our normal or support force. Hence we get Fn equals Fw, where Fw is the weight force. And that's basically what happens when you stand on your bathroom scales in the bathroom. You've got your weight force acting down and the scales are acting against you. However, if we want to accelerate upwards, then what we get here is a scenario where on the scales we've still got weight force acting downwards, but if we're going to be accelerated upwards, the scales actually have to push against us. So in this case, we're going to have the support force has got to be greater than the weight force. So the acceleration will be made up of two components. We've got the support force minus the weight force, or the force caused by the acceleration will be equal to the support force minus the weight force. So we get a difference in those two components. Now remember, they're acting in opposite directions, so hence that's why we get the negative. Now if we're going to be falling downwards, then it turns around the other way. So we're going to have weight force being greater than the support force on the scales. So in this case, we have to turn our equation round. So the force of causing the acceleration, or the net force, will be made up of the weight force minus the support force, because it's obviously going to be acting in the opposite direction, and the direction downwards will basically show us the positive being down and negative being up. So hence we get the two scenarios for accelerating upwards or falling downwards. Now the final thing we get is free fall. Now in free fall we have no support force, which basically means you're in a constant state of motion down. So as a result, the scales will register 0 because there is no support force acting against our weight force. As a result, your scales will read 0, which means that in this case you can be weightless, and this is solely due to the acceleration due to g, okay, which is down to gravity. So these four scenarios can be applied to a variety of different setups, and what you've got to be able to do is to be able to work out, well, if I'm pulling in this direction and there's a force acting in the opposite direction, I'm going to have to take those forces away, and what's left over will be the net force. If I know my mass and I know my net force, I can then work out my acceleration using F equals ma. If we're working on a plane, a horizontal, obviously if we're working upwards, then we'll be working with g. So as a result, we can use these little models to actually apply a variety of different scenarios. So just to recap, just to round off, the final bit that we can talk about free fall is the concept of terminal velocity. Now terminal velocity, if you jump out of an aeroplane with a perfectly good parachute but don't open it, what will happen is eventually you will reach terminal velocity. In this case, acceleration will begin to grab hold of you and pull you down at 9.81 meters per second. But friction from the air particles will start decreasing that acceleration until eventually your acceleration will get to zero. So it's as though the force of gravity pulling you down is counteracted by a friction force acting against you. The result is you will not accelerate anymore, so the force will actually decrease. You'll be going at a maximum velocity, but F equals ma won't apply because acceleration has got to zero, because it's been counteracted by the force of the air particles moving past you. So hence you reach terminal velocity, at which point you will not get any faster whatsoever. Now, the acceleration of an object on the planet Earth, as we know, is 9.81 meters per second, but this changes the higher you go up. Now, why is that? Well, because the force changes as we go up. And as you study your physics a little more, you'll come across Newton's law of inverse square law, which basically states that the higher you go up, and we're talking about really the radius of the Earth, which is 6,400 kilometers, the more radius you go out from the Earth, the acceleration due to gravity will decrease, and it follows this curve where basically we follow this inverse square curve. Now, as you move from planet to planet, you'll find that the acceleration due to gravity changes and gets either less or larger depending on the type of planet. So as I stated earlier, the acceleration due to gravity on the moon is 1.63. It's a lot smaller, so the result is it has less of an effect on a body, and that's why when we saw photos of Neil Armstrong walking around, he's sort of bouncing and he's sort of floating through the air. Not that there's air on the moon, but he's floating across the surface because there's not enough gravity grabbing hold. Okay, well, I hope that makes sense to you with respect to Newton's three laws. This is more of a theoretical process. What I'm also going to do is to put up some videos, some worked examples of how we can work through some scenarios using these three laws and applying the scale models which I showed on the previous slide. Okay, well, thank you for watching, and look forward to you joining me again. Bye for now.